Hey everyone, and welcome to today's Explainer. I am absolutely pumped to guide you through this fascinating material today. Okay, let's dive into it. We are looking at one of the most exciting, mind-bending, and honestly, kind of frustrating technological frontiers of our entire generation: quantum computing. We're going to unpack the incredible promise of this tech, the gritty problems holding it back, and the actual realistic path forward that researchers are charting right now.
You've definitely seen the headlines, right? It's the massive elephant in the room. We've got the underlying math beautifully figured out. We have these brilliant algorithms that promise to literally change the world. So, where's my desktop quantum computer? Why isn't this technology everywhere already? Well, that gap, that tension between the incredible theoretical hype and the really noisy, fragile reality of building actual hardware, that's exactly what we're exploring today.
And to answer that question, today's explainer isn't just based on some random opinion. It's actually distilled from a massive, systematic analysis of over 150 critical studies. We're talking papers published between 2010 and 2024. Researchers have rigorously synthesized foundational theories, algorithmic developments, and hardware progress over the last 14 years. So we are looking at the absolute cutting-edge consensus of where this field actually stands today.
Section 1. The Quantum Computing Promise.
So why are governments and massive tech giants pouring literally billions of dollars into this? Like, what can quantum computers theoretically achieve that our current classical computers simply can't? Well, it all boils down to these fundamentals. By exploiting superposition and entanglement and running processes through unitary evolution, qubits basically bypass classical logic entirely. This theoretical bedrock is what allows for massive exponential computational speedups. It lets us target previously intractable problems. Think complex molecular simulations for breakthrough drug discovery, or inventing entirely new materials that would take classical supercomputers millennia to figure out.
But here is a super fascinating twist. Entanglement is actually a double-edged sword. Yes, high entanglement is the exact resource that accelerates our computing power. But it is also exactly what makes classical simulation and system control so incredibly difficult. It's this crazy, delicate balancing act. The very thing giving the system its immense power makes it incredibly stubborn to actually manage.
And that brings us to a really surprising gap in the research. Despite our robust mathematical models, there's still a glaring lack of direct experimental validation for core quantum postulates at the physical level. It's like we're building these massive theoretical castles, but scientists are still out there highlighting the need to empirically validate things like entanglement and superposition in scalable physical systems. We absolutely have to distinguish the mathematical abstraction from the gritty physical reality.
Section 2. The Hardware and Noise Reality. If Section 1 was the dream, Section 2 introduces the primary antagonist of our story: decoherence. Listen, quantum states are incredibly fragile. Think of a quantum calculation like trying to maintain a deep, complex, whispering conversation, but you're doing it in a chaotic, crowded, and extremely noisy room. Any environmental noise, any slight change in temperature, what we call thermalization, and boom, that delicate quantum state collapses. The computation is completely destroyed. Now, what's really interesting about this slide is the stark contrast we're facing. On the left side, we have these beautiful, world-changing theoretical speedups, like Shor's algorithm for cryptography or Grover's algorithm for database searching. But then, on the right side, they hit this absolute brick wall of hardware constraints: qubit fragility, thermalization, crosstalk, which is basically when qubits accidentally interfere with each other. It is the ultimate clash between perfect theory and very imperfect physical reality.
Section 3. The Error Correction Bottleneck.
So if the environment is constantly going to cause errors, we need a way to correct them on the fly, right? Well, the reality of quantum error correction, or QEC, is a bit sobering. Researchers have developed these amazing mathematical frameworks, like surface codes and LDPC codes, to detect and fix errors. But here is the critical point. The resource overhead is absolutely staggering. Just to create one stable, reliable, logical qubit, we currently need millions of physical qubits to handle all the error correction going on in the background. Millions! And frankly, that far exceeds our present hardware capabilities. We just don't have machines that big yet.
Since we can't do full fault-tolerant error correction right now, what do we do in the meantime? Well, we use near-term error mitigation strategies. Since true fault tolerance is just way too resource-heavy, scientists use these stepping stone techniques to filter out the noise on our current flawed devices. We're talking tricks like zero-noise extrapolation, probabilistic error cancellation, and even neural error mitigation, which is basically using AI to help clean up the messy quantum data. It's a brilliant workaround while we wait for the hardware to catch up.
Section 4. Hardware and Software Co-Design.
This right here is the climax of our technological narrative. Researchers aren't just sitting around twiddling their thumbs waiting for perfect hardware to be invented. Instead, they are actively engaging in hardware-software co-design. What this means is they're dynamically shaping the software algorithms to fit the specific flaws of the noisy hardware we have right now, often called the NISQ era, or Noisy Intermediate Scale Quantum Era. They are actively tailoring how the software compiles and schedules tasks to literally dodge the specific noise profiles of today's quantum chips.
And this brilliantly illustrates how integrating those algorithms with actual hardware constraints dramatically reduces our resource requirements. Instead of demanding an impossible number of physical qubits, co-design significantly improves our computational fidelity using the hardware we have sitting in the lab right now. It gets us closer to real results without needing a computer that's, 50 years in the future.
Section 5. The Path to Quantum Advantage.
All that incredible ingenuity paves the way for bridging the final gap. Derived directly from those 150 source studies, these are the exact, targeted battlegrounds researchers are prioritizing right now. First, QEC scalability. We desperately need more resource-efficient codes and hardware-aware schemes so we don't need those millions of physical qubits. Second, simulating complex open environments, non-Markovian dynamics, requires us to build hybrid quantum classical algorithms that can actually share the workload. And finally, solving complex fluid dynamics and nonlinear PDEs means we need to integrate scientific machine learning directly with our quantum circuits. These are the specific trenches where the future of computing is being fought for right now.
To wrap things up, I want you to consider this profoundly interesting thought from the source material. Quantum mechanics is fundamentally linear, but the real physical world, turbulence, weather, chaotic systems, is highly nonlinear. So the ultimate question is, can we force the fundamentally linear universe of quantum mechanics to solve the chaotic, nonlinear problems of our physical reality? It's a question about the very physical limits of our universe. I really hope this deep dive has sparked your curiosity as much as it has mine and leaves you eager to learn more about the incredible quantum journey ahead.